Welcome to the sixth video in our course of learning general relativity. Well, so far we have seen how time and space are unified in a single structure. This structure has rules encoded in a matrix that tells us how distances and intervals are measured. Some entries are large, some are zero, and that tells us how different directions, including time, relate to each other. Today, we use these building blocks to better understand how the geometry of this flat space-time sets the stage for everything, from motions to measurements, before we introduce curvature and gravity. My name is Shaunak and you're watching this video on my channel, Physics for Students. Welcome to the sixth video in our course of learning general relativity. Well, those who have missed the previous 5 episodes, I would strongly recommend go ahead and check those 5 episodes. Well, the last episode has been very important. However, here is a quick recap on the most important part so that you really don't miss on something very important and we can have a quick understanding of what is called metric and space-time interval. Well, in the last video, I have explained that the structure of special theory of relativity is basically in Minkowski spacetime is something which is flat and which is not curved by gravity. And the geometry that we use to measure the distances is something looks like this. And here the obvious question comes that what is this equation? In short, it tells how distances and times are separated in a four-dimensional world of space and time. Now, if you look at ds square, it is nothing but the space-time separation between two events. Think of it as the distance in a four-dimensional space-time, but it is not like usual distance in space, but it also includes time. So here you can see also there is something which is called a dt, which is the difference in time between two events. So think of it as tiny difference in time in 4D space-time. These dx, dy, dz are nothing but the differences in space between those events. I would say infinitesimal small change in the quantity, and c obviously shows what is called the speed of light. Now, as we move further, we have also seen in the last video that this one is basically called a space-time interval. In geometry, in general, it is called the space-time interval. So it is basically how to measure distances or intervals. And in Minkowski space, the metric is designed to reflect the principles of special relativity. So obviously, we deal with is called the speed of light. Considering the speed of light as a unit quantity, c equals to 1, the equation reduces and looks simpler like this. So from here we come to know something very strange, which is called this minus sign, and we will explore today what is this minus sign. In general, it is called the intervals are time-like, space-like, or light-like. So the minus sign is basically the key. It makes the geometry more non-Euclidean rather than Euclidean. So this ds square is basically the space-time interval, and this is squared because it represents two events in space-time. The Minkowski metric that we have seen is moreover in a tensor form, and what it tells is that how to compute inner products or intervals between four vectors in space-time. Well, here comes the confusion which we cleared in the last video. What is the difference between space-time interval and Minkowski metric? So the simple answer is metric is basically a tool that tells you how to compute distances, and space-time is basically the interval is basically the distances computed. We went through an example. For example, there are two events which are happening. Event A at t1 equals to 0 and x1 equals to 0, and t2 is t2 equals to 3 and x2 is equals to 4. Then in order to find the Minkowski metric with a two-dimensional space-time, we are using not a four-dimensional, rather a two-dimensional space-time. I mean to say 2 by 2 matrix to make things easier. So the compute the coordinate differences, we use the metric and we find something like this, where this 7 is nothing that the space-time interval which is space-like and it is positive. So from here what we can say that you use the metric, the rule, to compute the interval, which is the result. We also have demonstrated that if we use a similar example using linear algebra, then if we take this one and then we take a usual dot product where g equals to I, that is I would say identity matrix. In order to make things easier, we get something like this, which is 25. So this is nothing special. It is just computing the length squared using the Euclidean matrix. Now the thing is that if you change the metric, for example, if I change it to this, where g equals to diag minus 1 comma plus the plus 1, then it gives something like this. So what we have seen here is that it is the same vector but using different metric gives different length. From here what we can get is that metric defines how to compute the dot product, and the result of the dot product is the value of the interval. From there we got several good conclusions, that the Minkowski metric is a constant tensor. It tells how to compute the distances, depends on the convention, that is time in seconds or space in meters, and you can assume that to be a rule that tells how to measure it. And from there we can say that this space-time interval, it is a result, it is a scalar quantity, it is measured in distances, typically length square and time square, and the length you read off the ruler. And from here we get that space-time interval is a measurement that you get, and Minkowski tensor or any form of a tensor is like a ruler. So here is a comparative study which tells that it is a tensor, that one is a result is a scalar. Rule is that it tells how to measure distances, it is the measured distances. Example is this one which I have just shown, and the analogy shows that the roller or the dot product, and this is actually the length you read off the ruler. So we paused and we ended the last video here. This is a quick recap so that the concept between metric and space-time interval, which will now come up quite often in the upcoming few minutes of the video, you won't get confused. So now we move in the today's video, taking ahead with this concept, that we are going to really look into a little bit deeper in what is called the Minkowski metric, because this is fairly important, and only when we understand the flat space-time better with all its components, etc., then we can go into the further complications of general relativity, which includes a tensor which has not the flat time but the curved space-time. So as we see, the Minkowski metric looks something like this, and the space-time interval as we have seen earlier. So this eta, this Greek symbol, actually denotes that it is a flat space-time. This is the space-time interval which we have just seen. Now here something is noticeable. You can see here is a -1 and we have got minus c square. So considering c to be equal to 1, that is, I'm taking the natural unit, we get a minus over here. We get a plus over here, we get a plus over here. We get a plus again over here, we get a plus again over here, and so on. So from here what we can say that these numbers actually do not vary with the position. They are actually same at every point. That is why they are actually 0. So the components are constants, you can see, and it behaves more or less like a Pythagoras' theorem, with a little exception that it has got a minus sign, which we are going to take a deep look why this minus sign is so very important. So basic idea that I wanted to tell you is that the signature that we follow, minus plus plus plus, it is the same that is in the metric tensor or the tensor format. We get the same. So that is why the tensor sets the rule, and interval is basically the actual thing which is measured. So from here we can say that the curvature of space-time derived from its 0, and these numbers do not vary, so it is flat. That is why the components are little bit, I would say, pretty, these are constant. So that becomes pretty important. Now this is actually the value of the Minkowski metric. But what about taking the signatures and finding the metric from this kind of a video? So this kind of a figure. So indicate the position of the matrix. So on the left hand side, what you can see, eta 00, eta 01, eta 02, these are the positions, and corresponding to each of the position on the right hand side, this is the matrix which shows you the value. So from here you can see that this is a 4-dimensional space-time metric, and eta mu nu, this mu and mu nu is basically ranging from 0 to 3. These are nothing but the coordinates. So 0 is the time, 1 is the space x, 2 is the space y, and 3 is the space z. So we have got 3 spatial components and 1 temporal component, which is the time component. So from here what we can say that each component of this eta mu nu, that means the space-time indices 0 to 3, tells you that how the muth and the nuth component, I would say the directions, are related to each other. That means what? That if I say that mu equals to nu, it is a diagonal component, that is the self-scaling, obviously. And if mu is not equals to nu, that means obviously it is an off diagonal component. That means it shows you the interaction between the distances. So that is why it is important. So as you can see here, that if I take this value, this is indicate the which position it is were. So eta 00 means -1, eta 11 equals to eta 22 and equals to eta 33. This is equal to 1, which is the spatial components normally. So from here what you can understand that all the off diagonal terms, that is eta mu nu equals to 0, for eta not equal to for mu not equal to nu, actually they indicate orthogonality. I will just show you what it means in a time, and then you will understand the value. So we turn the page, and what we can say, for example, here you can see, this is just an example. Eta 1 2 means second row third column, but remember one thing, that the counting actually starts from 0. So that is how it is. So you take 1 2, it means this, you take 1 3, it means this, and so on. So here you can see, if I take the first value, if I take eta 00, we have already seen it corresponds to this one, which is -1. So it tells that it is basically nothing but it is the time component, and it tells how to measure intervals in time. We will come to this a little bit deeper later. So the minus sign actually shows that how it has got a different role. The time has a different role in special relativity. Now if you consider this one, the yellow one, eta 01, now it corresponds to 0. To this value. So what does the eta 01 tells? It tells that time and x are orthogonal, and they are no mixing with each other. I will come to this part a little bit later. Just showing you samples. Now if I suddenly go to eta 11, which is this blue one, it corresponds to this one, which is again a kind of a value, which is 1, and this tells that it is an xx component. That means they are going in this direction. Again, say suppose I take a eta 1 2 value, then it corresponds to this. This tells that x and y, I would say, yeah, x and y directions are orthogonal. If I take eta 2 2, then it corresponds to this value. And what does this tell? It tells that it is the yy component. And then I go to eta 30 and so on. It is calling the z component. That means z and time are orthogonal. Eta 33 corresponds to this, and it tells what? That it tells that this is the zz component. That is the 33 values. So 33 tells that it scales in the z direction. So remember from here what we can say, that eta the mu is equals to 1, row 1, and nu equals to 2, that is column 2. So here you can get the mu as the row number which goes in this way, and nu is basically the column number which goes in this way. Now this is overall, but I haven't explained in deep what actually 1 0, the diagonal and off diagonal means. Well, before going that, I would first like to explain you what are the off diagonal components. That means in this matrix format, those which are not diagonal, what do they mean? And they really do carry a lot of meaning. So here you can see that I am taking again the same matrix, and I am trying to explain what is called the off diagonal components. So here when I look in this, all those, let me show you again. Yeah, this one. These are all the off diagonal components. So first, because all of them are 0, that means it indicate no mixing between different direction. What does that mean? It means that the time t does not mix with x, y and z. This is truly very important, so that you can understand that how time is differently behaving. That means that the coordinates are orthogonal. Obviously, just like Cartesian coordinates in flat space, they are 90 degrees. It follows the same rule. It is in base. So when I say orthogonal here, what does this orthogonal means? That means there is no mixing between axes. So if you move along, a movement in x-axis really doesn't have any effect on the y-axis and so on. So typically in Newtonian mechanics, we used this one. This is the 3D Euclidean space, and we get something like this. So here what we get in Newtonian mechanics, remember dx and dy are independent, x, y, z axes are perpendicular, and the geometry is flat, right? And that is what I'm trying to mean. This is orthogonal. So in a flat space-time, Minkowski space-time, there exists a coordinate system, but the metric looks like this everywhere. That means constant and diagonal. And there is no mixing, very important, and this means that the coordinates are orthogonal, just similar to the Cartesian coordinate. Now, I would like to take a step back, because this is important. I would like to explore the meaning of orthogonality in basic geometry. So in Euclidean space, or whatever say flat space, two vectors are orthogonal for example, when their dot product is 0. Very simple. We take A 1 0 and B 0 1 and we calculate the dot product, which gives you a value like this, 0. So that means they are perpendicular, orthogonal. Now if I take another vector, say for example 1 1 and 1 0 and calculate a dot product, you get 1. That means it is not equals to 0. That means they are not orthogonal to each other. So all in all, what we can say, which is very important, orthogonal means that there is no overlapping, no influence in each other, no shared component, and there are as different as two directions can be. Similarly, you can recall that u dot v is 0 because theta of 90 degrees, that is the cosine, is 0. But here is an important thing, that when the dot product is 0, it is like the similarity is 0. There is no projection of one to the other. Here I would like to ask the viewers, if you really know, there is a difference, a subtle difference between what is called a orthogonality and a perpendicularity, or I would say what is orthogonal and what is perpendicular. They are not the same, but we use those terms interchangeably. What is orthogonal and what is perpendicular? If you really know, you can let me know in the comment box. However, at this point of time, this is something which is important, that why the dot product is 0 and what does it mean. Now here you can see that this actually means what? It means that the coordinate axes are orthogonal, just like x and y. For a better visualization, here you can see that this is the t and this is x, y and z. So in Minkowski spacetime, they are not mixed, they are perpendicular. Each 0 of diagonal component means that they are independently moving. Now if the metric had values, that means if the eta 0 I, I mean to say 1 2 3 whatever up to I is not equals to 0, then would have happened, then time and spaces should not be orthogonal, right? And the coordinate system would have been skewed like a rotating frame or a curved space. We will soon look in this, what do I mean by skewed one and how things change. But this is orthogonal, the values are 0 and it is not skewed. But here is a quick point which I would like to tell you, that remember that orthogonality does not mean time and space are completely different. It means that they are independent directions in space-time, but they are still part of the same unified structure, which is called the space-time manifold or the space-time continuum. The reason Einstein united space and time in one continuum. So special relativity unifies time and space in a 4D continuum, even if the coordinates are orthogonal. Now this might sound a little bit abstract, we will explore this later. But remember once that orthogonality actually does not mean that they are independent. They are actually unified in a structured space-time, yet mathematically they are different, so that time and space can be calculated differently. It's the time now. Let us look in this part of the what do I mean by the skewed metric and the straight one. So if you imagine this one, this is a standard Cartesian coordinates, right? And the angles are 90 degrees. In that case, if I take a person who is moving in the x direction, he would move like this, this, this and so on. So that means every movement along x-axis does not change anything in y, because y is equals to 0. Now this is a skewed matrix. For example, the x is little bit tilted, whatever be the reason. Now here you can see every time the person moves at the x-axis, makes a change in the y-axis. Further, makes a change in y-axis. Further, makes a change in y-axis. So movement along x is slightly moving along the y because the axes are not orthogonal. So in Minkowski spacetime, the left case was true, but as things curved, it won't be orthogonal. So what we get from here is that time and space coordinates actually are orthogonal. The coordinate grid lines are not skewed, and the time is flat. Then the geometry is what is called pseudo-Euclidean. Now here is a point I would like to explain why we call it pseudo-Euclidean. We'll come to that part soon. On the other hand, for example, if I get a metric like this, let us forget what are those. But here you can see the diagonal and the off diagonal, they have value 0.5 r square sine square theta. What does that mean? That means the off diagonal component equals to 0.5. That time and space are mixed and they are basically a skewed coordinate system. That means every movement in x would take a change in the movement of y. This is for the flat space-time. That means it has got a value. And that is the reason we say that special relativity is much easier, considering the complexity of mathematics, etc. easier. Why? Because it has got no value. So it is constant everywhere. But as soon as you start getting the values, the movement would make changes. So this is what is called the value. Now, as I told you, I have written in red that why do we call it pseudo-Euclidean, not purely Euclidean? What do I mean by that? Let me give you a quick example, because pseudo-Euclidean, pseudo-Riemannian, these things are very common in learning general relativity. So, if I take literally, pseudo means false or almost. So, pseudo-Euclidean space is one where, for example, if we take the standard Euclidean space, we use the Pythagoras' theorem, dx square plus dy square plus dz square. And in case of a 4-dimensional, we use another coordinate dt, but things remain the same. But in special relativity, we use this minus c square dt square. Or equivalently, using the natural unit 1, we get this value. And also the metric would look like this, something like this. The signatures are minus. You see the minus 1 and plus plus plus. And this is used mostly, as far as my knowledge goes, in the books of Landau, Misner, Thorne and Willer. And here you get a positive one and then 3 negatives. And this is something plus, minus, minus, minus. And this is used by Steven Weinberg and some other quantum field theory books. It's the convention, but this convention also have a very deep meaning. We will come to that. So this is what is the Euclidean space and then in the Minkowski metric. But remember, both these are right. So I have put a green tick over that. Both of them are right. It is a matter of convention. So if I take Gij, for example, if it is a Euclidean, then each one number of the diagonal tells us the scaling for each coordinate. If I take the Minkowski, the matrix is still diagonal like in Euclidean, but has got a time component, this one, which has got a negative sign. That means what? That means, first of all, the metric is not positive definite. Obviously, it has got a negative one. Distances behave differently. We will see that why it is called light-like, time-like and space-like. And both the signature of the metric contains both positive and negative terms. And as you can see here, now we come to the real reason. We call Minkowski metric as a pseudo-Euclidean. Why? Because it resembles, as I told, it is false or almost like. It looks almost like Euclidean geometrically, structurally, but it has got an exception, that has got mixed signs. And this change in sign is introduced, the pseudo part. So it is not positive definite anymore. So the space is not positive definite. So here you can see that the Minkowski metric is a pseudo-Euclidean space with a metric of 3, 1 or 1, 3 depending upon the convention. Here 1, 3. Why? Because 1 negative and 3 positive, plus, plus, plus. And here the convention is 1 positive, 3 negative. So we call it 3, 1. So all in all, what we can understand is that pseudo means it resembles, it looks almost like Euclidean space with this type of deviation. Mixed signs, introduce, space-time is not positive definite. Now let us dive in this part of the video. It is a good time that we look in the real meaning of the components of the Minkowski metric. That is what we actually started with. So if you take the Minkowski metric as something like this, I'm writing the eta and the values so that it is easier. So we will first take what is called the mu nu. We have already told you these are the indexes of space and time, 0, 2, 1, 2, 3. Now we are taking this one, right, for the first row. 0, 0, 0, 1, 0, 2, 0, 3, and let us explore first thing. So the row 0 is basically what is called the time axis. I will explain it what means. So first let us take this one, this value. I think we have explained it a couple of times, no need to go again further. This 0, 0 and minus 1, this comes from here. And this is what is called, I would say, it is called time and space directions are independent and orthogonal in phase space time. Now say for example, if I take a person, for example this person, right? So this person in real life times I'm explaining, you're just sitting, okay, in one place and your space coordinates are not changing. How will it do? Because you're sitting. So from here what we can say that dx and dy and dz are 0. Because time they are not walking, you are not walking or running. But as you see, even if you sit, the time changes, t0, t1, t equals to 1, t equals to 2, t equals to 3 and so on. So this is what this part first 0, 0 actually tells. That if dx, dy, dz, you're not moving, so spatial coordinates are 0. Time is not 0 because time is ticking. It is 0, 1, 2 and 3. So this is what is called a pure time difference. That means space is not dominating this time. It is only the time which is dominating. So time is still passing. And hence, if we take the time part and if we eliminate x, y, z, say for example in the left hand side equation, if you eliminate dx and dy and dz because they are all 0, what it will lead to? It will lead to ds square equals to minus 1. C square dt square I will explain later, but it is minus 1. And that is why this is called a time-like interval where the motion only is through time because you're sitting and you're not moving through space. And that is what the sign minus 1 comes. I hope this can make the first component quite clear. Now let us look at the next component. The next component was eta 0, 1 which corresponds to 0. Now what does this 0 means? It means there is no mixing or coupling between the time coordinate and the space coordinate. So here again the same analogy. The person is moving. Eta 0, 1 equals to 0. It means there is no tilting and the time and space are absolutely clean and clear. So there is no mixing or coupling. Time and space directions are independent. On the other hand, if this x coordinate have been a little bit tilted, skewed, that means eta 0, 1 would have not been equal to 0. So eta 0, 1 equals to 0 means time and space directions are independent and orthogonal in flat space time. So it means moving in time does not affect your position, moving in x direction does not affect your flow through time, and they are orthogonal directions in the geometry of space and time. So when we are talking space-time, I understand it's a 4-dimensional space-time, very difficult to imagine, but I will give you a simple figure to imagine. This is what we are talking about. So you see time going in some other direction, we have got x and y and z, and these are the components that we are looking. So now you see that this one we have already discussed, this one we have already discussed. This actually means I'm using the perpendicular sign, but remember what I'm trying to tell, this one is basically t and x are orthogonal. That means no mixing. Again, this one t and y are orthogonal. This one t and z are orthogonal. Remember, I'm not considering the diagonal components for a reason, only taking minus 1 at the top. Again, I'm coming to 0. X and t are orthogonal. X and y are orthogonal. X and z are orthogonal. Coming further, you see y and t are orthogonal. Y and x are orthogonal and y and z are orthogonal. Similarly, z and t are orthogonal, z and x are orthogonal, and then we find z and y are orthogonal. So all in all, if you consider overall, we can say that if I am asking this question, for example, that does walking in this direction also move me in some other way? So the answer is strictly no, because everything is independent, cleanly aligned and orthogonal to each other. So this is what actually it means. So if I take a fresh page now, you can see this one is the rho 0 time axis, which means rho 1 x axis, rho 2 y axis and rho 3 z axis. And here what the metric is telling is how to measure the length of that movement. Basis vectors, remember, in these two directions are perpendicular. So yes, they express the same geometric idea, no direction, no leaning, no mixing of coordinates. So overall we can say that the Minkowski metric is not about the motion of an object. Remember that Minkowski metric doesn't actually tell you what is the motion. It is actually the geometry of space-time. That means how distances and angles are measured in that space. Now one thing is very remarkable in Minkowski space-time. If you look at this one, you can see that there are certain things which are, I won't say common, but they can be taken as a pair. For example, this 1, 0 and 0, 1. I will come to what do I mean by pair, because this carry a meaning. This one. So 1, 0 and 0, 1 equals to 0 means x and time are orthogonal. Similarly, 1, 2 and 2, 1 can be a pair. X and y are orthogonal. Similarly, 1, 3 and 3, 1 can be a pair. And 2, 0 and 0, 2 can also be a pair, as well as 2, 3 and 3, 2. So remember, when we talk, these are not cancelling out, right? So 1, 2, 3, 4, 5, 6. We get 6 components that they don't really cancel out. The word cancel doesn't work. It actually means that we are not counting 1, 0, 0, 1, 0, 2, 2, 0, 1, 2, 2, 1 and so on. Because why? Because they are we don't take into account due to the symmetry. So all these 6 off diagonal components are exactly 0. That means they are not contributing to the metric. So that is the reason we are not counting. Why this is important? Because now you see we get 6 pairs, isn't it? 1001, 1221, 1331, 2002, 2332 and 3003. And in similar way, if I take the metric tensor of general relativity, which is obviously not flat, okay, here also you get the same 1001, 0220, 0330 and so on. Here also we are getting the 6 pairs, you can see. So we are not cancelling, but we are taking it as a pair. So that means both of them are not counted in Minkowski metric. But in case of general relativity it will be, but still we are getting 6 pairs just to show you that these are symmetric tensors. So here is a quick calculation. Total components 4 times 4, 16. How many diagonal components? 1, 2, 3, 4. Obviously it's a 4 by 4 metric. And the off diagonal 12. Independent 6. So total independent components 6 plus 4 equals to 10. And that is the reason we say that this is the Einstein field equation. In Einstein field equation, these are symmetric. The stress energy momentum tensor, the Einstein tensor, the metric tensor, and that is the reason you will see in several videos, even I have talked that the Einstein field equation consists of what is called 10 independent equations. Sorry. Why it is 10 independent equations? Because we are not considering these 6 pairs. Because why? Because they are symmetric. Now, what is the meaning of a symmetric tensor? That is a different issue. I will come to that part later. So that is what I was telling, that remember that the pairing happens due to the symmetric nature of the tensor. That means if you swap the indices from mu nu to nu mu or AB to BA, the values actually do not changes even if you swap the indices. So a symmetric tensor is something that satisfies T mu nu equals to T nu mu. So if you can imagine a square matrix like this, A, B, C, D, E, F. So you can see this B and B is where T01 equals to T10 and CC is where T02 equals to 20 and so on and so forth. So the symmetry across the main diagonal is exactly the same as tensors. Now you might say that what are some of the examples of symmetric tensors? For example, geometric tensor, very much symmetric, stress energy momentum tensor, Ricci tensor, and inertia tensor, which is used in I would say in the Newtonian mechanics. But have you noted one thing which I now highlight with a red line? All of this contains the same indices mu nu, but why do inertia tensor has got a ij instead of mu nu? The exception is because in all the entire world of relativity, we always use mu nu in order to denote what is called the indices of the space-time. Now, in order to differentiate from relativity to a non-relativity classical physics, we are using ij. You know that in general physics also we say the ith component, the jth component, are using I as a test particle. You are aware about that. So that is why we are using ij, not mu nu, in order to strictly denote that this is a Newtonian world that we are dealing, not a relativistic world. So this is what is called the meaning of the components. Now here is a time that we should do a quick summary before we move on to the next topic. So what we have learnt is that Minkowski spacetime is equals to flat spacetime. These are the coordinates. Minkowski metric is denoted by eta mu nu, that actually tells what are the distances and angles that we find out. We also find that the diagonal components show self-relations and off diagonal components are showing orthogonality. That means time and space, etc. Next, what we have learnt is orthogonality and coordinates. So in Newtonian Euclidean space, orthogonality also applies, like walking north, east, etc. We also understood what is ds squared, that is the space-time interval, and you also have seen in the last video what is the difference between, here also, difference between space-time interval and what is called a Minkowski metric or a metric tensor. Negative ds square means time-like, a person sitting in a place. Positive means space-like, events at different places, and 0 is light-like, that is the path of a ray of light. We also have seen there are 2 types of vectors. We have seen contra. Yes, I know that we have not seen covariant, which we will explore in the next video. This helps to convert between the 2 types of matrix via raising and lowering the indices. Symmetric tensor, we have seen how swapping of the matrices actually doesn't make any difference in the measurement, and flats and curve space-time. That means Minkowski space-time deals with something which has got no gravity, where GR, which has got gravity, makes things further complex, for example radial distance, etc. Now, as you have seen, there are certain things which I have not covered in this video. Among them, first is that this one, why it is a covariant vector, or we can say covariant tensor, because you can see the matrices, the indices are sometimes going up and down. This is what we will explore in the next part. In this space-time interval, you can see there is a negative sign. Why is this negative sign? Also, just behind the negative sign, why we are putting c square, what this c has to do, because we are just dealing with x, y and z, the spatial component, and time is the time component. So is c is related to something space or time? We really have not explored on that. Also, you will see I have not explored specifically what is time-like, space-like and light-like in a light cone. We have explored in the light video how a light cone evolves, but not all of this, which I am going to explore. And we have seen some books follow minus and then a plus, then some books follow plus and then minus. What is the meaning of these signatures? I mean to say how these signatures suddenly evolve and suddenly come. So these are the few things which I am going to explore and explore more in the coming video of general relativity in our course. So that's all for today's video. Thank you very much for watching this. If you have really liked the video, please do subscribe to my channel Physics for Students and click on this bell icon to get all the notification from Physics for Students. You can subscribe to my other channel on general relativity, and you can contact me for further clarifications over this email ID of mine. So Physics for Students will continue with some interesting podcasts coming up in this month. And keep watching and keep wondering about the mysteries and beauty of the universe. See you soon in the next video, but till then, may the good Lord be with you.